Okay, where we left off was with unit conversions of compound units. So units made up of two or more other units, like miles per hour or meters per second. And so this is a good example of how to convert units like this. What you really have to do is basically just convert the units in the numerator and then convert the units in the denominator. And you just do one after the other. You can do either one first, as long as you make sure that you do them both. So we're going to have to go from miles to meters. And to do that, you're going to have to stop off somewhere. Let's see, miles to kilometers would probably be the best way, and then kilometers to meters. That would be pretty easy. And then hours to minutes to seconds would probably be the best way to do the time. This is a conversion that you might want to do because, well, meters per second would be the standard units for speed or velocity in the SI system of units, whereas miles per hour would be the way we commonly measure speeds in everyday life. And so to do this conversion, you start out with what you're given, which is a speed of 65 miles per hour. And I find that it is very helpful to write these quantities out explicitly as one thing over the other. Even if it's given to you like this with miles/hour or mph, you really should write it as 65 miles over 1 hour, because you travel 65 miles in 1 hour. This will make it this will be very helpful when it comes time, especially to convert the units on the bottom of the fraction, because it makes it clear that these units are on the bottom. If you write it like this, miles/hours, it becomes much less clear what's on the top and what's on the bottom. And you really need to know that when you're doing these conversions. I'm going to choose to convert miles to meters first. And so that means that we're working on converting the unit in the numerator, and we're going to just completely ignore the unit in the denominator for the moment. So if we're going to convert miles to meters, and we're going to go by way of kilometers, then we would probably next want how many kilometers are there in a mile. Miles in the conversion factor would need to go on the bottom, so it will cancel out with miles here. And there's 1.61 kilometers for every mile. Miles cancel, and now if you wanted to stop and write down the answer, you would have kilometers per hour, because the hours are still there. We haven't canceled those yet. So kilometers per hour, but I'm going to keep going. There's no reason that you have to stop and write down the answer after every conversion factor. You can just keep right on going. So let's see, next we need kilometers to meter. Kilo means 1,000, so there would be 1,000 meters for every 1 kilometer. Kilometers now cancel, and if you wanted to write down the answer now, it would be in units of meters per hour. Because remember, hours are still there. Well, meters are the units we want for the numerator. That's why I'm circling them. But instead of stopping now and going on to another step, I'm just going to keep going. And now I'm going to come back and convert the hours. And what you have to realize, though, and keep in mind, is that hours are in the denominator of the fraction. That turns everything upside down. So when you're using a conversion factor, if the units you're converting are in the denominator, those units have to be in the numerator for a conversion factor. So if we're going to go from hours to minutes, we want hours to be in the numerator and 60 minutes to be in the denominator, because the time is in the denominator, and that's what we want to change. So now hours will cancel, and if we chose to write down an answer now, we would have it in units of meters per minute. But there's one more step, and that is going from minutes to seconds. There's 1 minute for every 60 seconds. And remember, you want minutes in the numerator because those units were in the denominator, and you want them to cancel. And you want the new unit to be in the denominator. And so now, if you multiply this out, you will have units of meters per second, because those are the two units that haven't canceled out yet. And to work it out, all you have to do is take 65 times 1.61 times 1,000. You can ignore all these ones. But now you come to a number where the number other than 1 is in the denominator. So that just means that next you divide by 60, and then you divide by 60 again. And we get 29.0694, and that would be meters per second. Now, for significant figures, we have to look at the significant figures. 65 only has 2 significant figures. 1.61 has 3. 1,000 meters per kilometer is a definition in the metric system. That's infinite. 1 hour for 60 minutes, that's an exact number. So that's infinite. 1 minute for 60 seconds is also infinite. So 2 significant figures it is. That means we can keep the 29, but everything else has to go. The first number we're dropping is a 0, which is less than 5. That means that the numbers we're keeping can stay the same. So 29 meters per second is what we end up with. Okay, so that's not a bad way to do things. Okay, units raised to a power are another thing that you have to know how to deal with. For those, you just normally use the same conversion factors as for the one-dimensional units. But you raise the conversion factor to the same power. All right, so you raise the conversion factor to the same power. If you're going to say, convert 1 inch to centimeters, you multiply it by the conversion factor 2.54 centimeters per inch, and you get 2.54 centimeters. If you want to convert 1 square inch to square centimeters, you use the same conversion factor, but you square it. And now you have to remember that this square here applies not only to the units, but also to the number. So when you're multiplying things out, you have to remember that. And the number of square centimeters in a square inch is 1 times 2.54 times 2.54, or 1 times 2.54 squared, which is 6.45 square centimeters per square inch. Okay, so 1 inch to the 3rd power. If you want to convert cubic inches to cubic centimeters, well, it's 2.54 centimeters per inch again, but you have to cube the conversion factor. But again, don't forget that the conversion factor applies not only to the units, but to everything in the parentheses, including the number. So it's 1 times 2.54 raised to the 3rd power, which is 16.4. So 1 cubic inch is 16.4 cubic centimeters. Okay. So that is basically how you handle that. And you just throw that into the conversion factors along with the other things, and you'd be done. There would be also the use of density as a conversion factor. Actually, we already saw that in some of the previous questions, so I'm not going to go over that in detail. And there's also a little section on rearranging equations, but that's basic algebra, and I don't think that we're ever actually likely to get something like that. So we're supposed to cover the first section of Chapter 2 during this lecture also. So that's what I'm going to do. I'm going to go on to chapter 2. If there are any questions about that last couple of entries in the last section of chapter 1, be sure to ask. You can send me an email and I'll answer right away. But I think that those are things that we're probably not going to encounter very often. So this is the beginning of chapter 2. The first couple chapters, chapter 2, the first couple of sections of chapter 2 are interesting to read over. They're pretty short, actually, and I'm not going to go over them in detail in class because we don't really have time for that this summer. So we're going to have to go right on into the meat of chapter 2, which begins with section 2.3. Which is about the modern atomic theory and the laws that lead up to it. And this includes the laws that lead up to the atomic theory, because atomic theory was actually developed in conjunction with understanding of some of the most important laws of chemistry, like conservation of mass and the law of definite proportions, and the law of multiple proportions. And all of these led to the development of modern atomic theory. And we'll see how that happened in short order. So as for conservation of mass was developed by Antoine Lavoisier in France, and he noticed that when he conducted a combustion experiment in a closed container, that the mass didn't change. And what he surmised from this was that the mass of the products of a chemical reaction have to be equal to the mass of the reactants. A somewhat fancier way of saying this is that matter is neither created nor destroyed in a chemical reaction. Okay. And basically what happens in a chemical reaction is that the atoms are rearranged and recombined in new ways. But you still have the same number of atoms of the same element. Okay, so for example, if you take carbon and oxygen from the air and you combine the two by basically burning the carbon, you end up with carbon dioxide. This is a very simple chemical reaction. And if you look at the masses of these elements in the periodic table, a carbon atom has a mass of 12. And actually, the group that we like to use of atoms, called a mole of substances, would have a mass of 12 grams for carbon. O2 would have a mass of 6, well, oxygen atoms have a mass 16 each, and 2 of them would be 32. And so together, the mass of a carbon and 2 oxygens would be 44. Well, over here, you have one molecule that consists of carbon and 2 oxygens combined with, bonded to each other. That one molecule has a mass of 12 plus 32, which is 44. So the mass remains the same because you've got the same number of the same elements present. So that's your law of conservation of mass. And now we have the law of definite proportions. And this is the case where Joseph Proust in 1797 found that the elements making up a given compound were always present in the same proportions. And this he was measuring things in mass. So the elements in a compound are always present in the same proportion according to mass, but it turns out that the same is true of the proportion of the number of atoms present. Okay. And the fact that the proportions of the elements present were always the same for any given compound, that's what we mean by definite proportions. A more formal statement would be that all samples of a given compound and I'm abbreviating compound here, all samples of a given compound regardless of source or preparation method have the same proportion of constituent elements. So that's kind of a more formal way of saying it. So for example, if you decompose 44 grams of CO2, you get 12 grams of carbon and 32 grams oxygen. The ratio of oxygen to carbon would be 32 to 12, and that's equal to 2.67 to 1. If you decompose, say, twice as much carbon dioxide, say 88 grams of CO2, you get 24 grams of carbon and 64 grams of oxygen. The oxygen-carbon ratio in this case would be 64 over 24, which is 2.67 to 1. So it wouldn't matter how much carbon dioxide you decompose, you always get that same ratio of oxygen to carbon. And of course, this also applies to the number of atoms. As we can see in the chemical formula, carbon dioxide is made up of 1 carbon and 2 oxygens. So in terms of numbers of atoms, you're always going to get twice as many oxygens as you have of carbons, no matter how many actual molecules of carbon dioxide you decompose. Of course, it wasn't found out until later that that applied to numbers of atoms, because in Proust's time, we didn't actually know that, well, they weren't actually certain that atoms actually even existed. The law of multiple proportions was conceived by John Dalton in 1804. And this can be stated as when 2 elements form 2 different compounds, the mass of one element combining with 1 gram of the other element can be expressed as a ratio of small whole numbers. Okay, so they were working with masses back then because, again, John Dalton is actually the guy who came up with the modern theory, well, actually the beginnings anyway, of the modern theory of atoms, but he didn't do that until a few years after this. So we didn't actually know for sure that atoms even existed yet at that time. So if you look at, for example, carbon monoxide versus carbon dioxide. Okay, so for CO, the ratio of oxygen to carbon is 1.33 to 1 in terms of mass. For CO2, the ratio of oxygen to carbon is 2.67 to 1 in terms of mass. If you compare these ratios to each other, 2.67 over 1.33 is 2. That's a small whole number. And this is what Dalton found out. He took that information that this applies to masses, and over the period of the next couple of years made the leap that if this applies to masses of the atoms, then it also must apply to some sort of small fundamental unit of those atoms, or of those elements, I mean. And that small fundamental unit came to be known as the atom. So Dalton's atomic theory which was finalized in 1808, is based on these previous researches by various researchers, and he postulated certain tenets to his atomic theory. And what's really amazing is that for something that was done more than 200 years ago, 212, I guess to be exact, is what's amazing is how much of it he got right. He was wrong about a few things here and there, but he got most of it right, actually. So he theorized that each element is composed of tiny indestructible particles called atoms. He postulated that atoms were indestructible, But that's why he called them atoms. In fact, atoms comes from a Greek word that means indivisible or can't be cut. Well, actually, as we know today, atoms are actually not indestructible. They can be destroyed as part of nuclear reactions, and they can be destroyed in atom smashers and things like that. But other than that, he was right. They are tiny, and they do compose all matter. He also said that all atoms of a given element have the same mass and other properties and they're different from the atoms that make up any other element. Okay? And actually, he was right about almost all of that. But as we will see in a later chapter, isotopes of an element do have different masses. But otherwise, he was right. He didn't know about isotopes yet because nobody, well, he was only just theorizing that atoms exist. Nobody knew about the subatomic particles like neutrons yet. And neutrons are what are responsible for isotopes. Okay, and he theorized that atoms can combine in simple whole number ratios to form compounds. That's true. I'm not even going to make any exceptions to that because it's true. He said the atoms of one element cannot be transformed into any other element by chemical reactions. Okay, and that's true, actually. That's part of the law of conservation of mass or conservation of matter, is that you have to have the same number of atoms of the same elements coming out of a chemical reaction as you have going in. And if atoms could be transformed into other elements, then that wouldn't be true. So atoms indeed cannot be changed into any other element by a chemical reaction. Now, nuclear reactions, on the other hand, they can transform one element into another, but Dalton didn't know about nuclear reactions. Nobody did yet. So by chemical reactions, cannot change one element into another. And in fact, the medieval alchemists spent about 500 years trying to do that to the best of their abilities, and nobody ever managed to do it. You know, trying and trying and trying to change iron or lead into gold. Sorry, not going to happen. And he also theorized that in chemical reactions, what happens is that atoms only change the way that they are connected to other atoms. And that really is basically what a chemical reaction is. You take apart the atoms as they start out, you rearrange them, and then you bond them back together into different combinations with other atoms. But the atoms themselves don't change. Okay, that is the end of section 2.3, and that is the end of this lecture according to the schedule. And we're right on time. So I'll see you next time. Bye-bye.